In this problem, we use the stiffness method to find member forces for a beam, and then we'll construct the shear diagram. The key concepts we'll use are calculating deformations for a beam, calculating member forces for a beam, and constructing the shear diagram for a beam given member forces and loading. And here's our beam. Fixed at node 1, rollers at nodes 2 and 3. It's a continuous beam. E and I are constant along its length. We are going to determine the internal shears at the ends of the members, and we'll use that information along with the loading to construct the shear diagram for the entire beam. Here's the approach we'll follow. We'll begin by approximating the answer. And then we'll use that after we construct our shear diagram from the stiffness method results in order to evaluate the reasonableness of our answer. Then, to begin the stiffness method, we'll construct the structure stiffness matrix. We'll compile the fixed end forces. Then we will find deformations. At the unconstrained degrees of freedom. Then we'll find member forces. Specifically the shears at the ends of the members. We use that to construct the shear diagram. And then we'll compare with our approximation. Let's begin. So we begin with step 1. Let's approximate the answer. To do that, I'm going to assume that the distributed load all goes to the nearest vertical support. That means, since this is the only region with distributed load, 1.5 meters worth goes to the reaction at node 3, and 1.5 meters worth goes to the reaction at node 2. So the reaction at node 2 in the y direction will be approximately the distributed load times the 1.5 meters over which it acts, and that's 15 kilonewtons up. The reaction at node 3 in the y direction will be approximately 10 kilonewtons per meter, 1.5 meters, so also 15 kilonewtons up. That means that reaction 1 at node 1 in the y direction will be about 0. Well, if we construct our approximate shear diagram in the units of kilonewtons, we begin at 0, and the shear diagram stays 0 because there's no applied load, so we have constant shear. And since the magnitude was 0, it stays 0. Then at reaction 2, it jumps up a magnitude of 15 kilonewtons. And then we'll have a linear shear diagram because we have a constant distributed load, and it will decrease starting at a magnitude of 15 minus the distributed load acting over 3 meters gives us a minus 15 kilonewtons. And then reaction 3 gives us a jump, so we have the minus 15 plus the jump of 15, that equals 0, and so that checks out because the shear diagram should close to 0. Now, about this portion being 0 and this reaction being 0, if we sketch the anticipated elastic curve, that is, the deflected shape, expect it to look something like this. Because it's fixed at this end, the slope must be 0, be concave up because of the downward distributed load. But in order for this shape to occur, we'll need a downward reaction. So I actually expect a small negative value here. Let's see. Now we're ready to begin the stiffness method. And we do that by assembling the structure stiffness matrix. To do that, however, I need to first obtain the member stiffness matrices. And so we'll start with member 1. And the member stiffness matrix is given by this 4x4 matrix shown here in equation 15-1. Notice that there are a lot of repeated terms, so let's pre-calculate those. The length of our member is 6 meters. 12 EI over L cubed will be 12 EI over 6 meters cubed, which will give us 5.56 times 10 to the minus 2 EI over meter cubed. 6 EI over L squared will give us 0.167 EI over meter squared. 4 EI over L will give us 0.667 EI over meters, and then 2 EI over L .333 EI per meter. And so let's assemble K1, the stiffness matrix for member 1. EI is common to all of the terms, and as we look at the sequence of degrees of freedom in this matrix, it's near node Y, which is degree of freedom 4, The near node Z, degree of freedom 3. Far node Y, degree of freedom 5. And far node Z, which is degree of freedom 1. Our rows will be associated with the same degrees of freedom, so we have 4, 3, 5, and 1. Our first row, first term, is the 12 EI over L cubed, so that is 5.56 times 10 to the minus 2 divided by meter cubed. I pulled the EI out front since it's common to all of the terms. Then we have the 6 EI over L squared. Then the minus 12 EI over L squared, or over L cubed rather, minus 5.56, 10 to the minus 2 meter cubed, and then 6 EI over L squared, 0.167 over meter squared. In the second row we have 6 EI over L squared, then the 4 EI over L, then the minus 6 EI over L squared, so we have the minus 0.167 per meter squared, and the 2 EI over L, 0.333 per meter. Then in our next row, minus the 12 EI over L cubed, 10 to the minus 2 over meter cubed, then minus 6 EI over L squared, and 12 EI over L cubed, and minus 6 EI over L squared. Then the 6 EI over L squared, 0.167, 2 EI over L, a minus 6 EI over L squared, and 4 EI over L, 0.667 per meter. Now we want to check, are the diagonal terms non-negative? And in this case they're all positive. That's good. We also need to check that it's symmetric about this axis. So these terms are alike, these terms are alike, these terms are alike, as well as these, and these terms are alike, and these terms are alike. So it's symmetric, and that's an important intermediate check, because if it was not, we would be able to identify right away that we've made an error. Now for member 2. The length of the member is 3 meters. So the quantity 12 EI over L cubed will give us 0.444 EI over meters cubed. 6 EI over L squared will give us 3 meters squared, 0.667 EI over meter squared. 4 EI over L gives us 1.333 EI per meter, and 2 EI over L therefore gives us 0.667 EI per meter. Now let's assemble that information into the stiffness matrix for member 2. And in this case, we have near node, far node. Our degrees of freedom are 5, 1, 6, and 2. So our rows are 5, 1, 6, and 2. And now for the entries. A quick peek back at equation 15-1. You might want to keep it handy. Says we'll start with 12EI over L cubed in the top left, then 6EI over L squared, then minus the 12EI over L cubed, and the positive 6EI over L squared again. So we have 0.444 over meters cubed because we pulled the EI out from all of the terms. And then the 0.667 divided by meters squared. Then we'll take a minus that term and a positive of that term again. Then our next row, 6EI over L squared, 4EI over L, a minus the 6EI over L squared, and then the 2EI over L. So it's a 0.667 over meters squared, the 4EI over L, then the minus 6EI over L squared, and then the 2EI over L. Then the next row is identical to the first row, but all of the signs are reversed. So we have 0.444 over meters cubed minus 0.667 over meters squared, and now a positive 0.444 over meters cubed and a negative 0.667 over meters squared. Then for our last row, 6EI over L squared, 2EI over L, the minus 6EI over L squared, and then 4EI over L. So 0.667 over meters squared is the 6EI over L squared, then 2EI over L is 0.667 over meter, then the minus 6EI over L squared, and then 4EI over L. And now let's check that our diagonal is all positive. It is. And that it's symmetric about that diagonal. And it is indeed symmetric. Now let's assemble the structure stiffness matrix. The structure stiffness matrix is given by capital K, and it'll be the sum of little k1 and little k2. But I want to point out, it's not just a 4x4 matrix. This summation is by degree of freedom. So capital K will be a 6x6 matrix. We observed when applying the stiffness method to trusses that if 2 degrees of freedom are not at the same node, nor are they connected by a single member, then the stiffness coefficient will be 0. So for example, the structure stiffness coefficient 2 3 will be 0 because degree of freedom 2 and degree of freedom 3 are not connected by a single member. And when we look at our structure, we see that only degrees of freedom 1 and 5 will receive contributions from each of the two members. So let's calculate coefficient 1, 1, which is the force at degree of freedom 1 due to deformation of degree of freedom 1, and it will be that coefficient from element 1 and that coefficient from element 2. And if we look back at our element stiffness matrices, from member 1, coefficient 1, 1 is not up in this top corner, but is instead row 1, column 1 by degree of freedom. It is this quantity. To which we add this quantity from member 2, row 1, column 1 by degree of freedom. Combined, those give us 2.0 EI per meter. Now coefficient 1.5, that is force generated at degree of freedom 1 due to deformation at degree of freedom 5. We'll obtain that by adding the coefficients from each of the two member stiffness matrices. From member 1, row 1, column 5 gives us this coefficient, and from member 2, row 1, column 5 gives us this coefficient. So we have a negative 0.167 EI over meter squared plus a 0.667 EI over meter squared, and together we get 0.50 EI per meter squared. And how about going the other way? Coefficient 5.1. Force generated at degree of freedom 5 due to deformation at degree of freedom 1. We add the coefficients from each of the two members, which are from member 1, row 5, column 1, this coefficient, and from member 2, row 5, column 1, this coefficient. So we have a minus 0.167 EI over meter squared plus 0.667 EI over meter squared, which gives us a 0.5 EI over meter squared. And coefficient 5.5. From member 1, we have this coefficient, and from member 2, we have this coefficient value. And so we have 5.56 10 to the minus 2 EI over meters cubed plus 0.444 EI over meter cubed, and together those give us 0.50 EI over meter cubed. I think we see how the process works, and we've combined all of the degree of freedom, or all of the coefficients that have contributions from both elements, And so let's focus on the structure stiffness matrix for the entire structure. We will do so in degree of freedom sequence 1, 2, 3, 4, 5, and 6. So the rows will also be associated with degrees of freedom 1, 2, 3, 4, 5, and 6. For coefficient 1, 1, we've already calculated that, 2.00. I'll pull the EI out since it's common to all of the coefficients. 1, 5 we've calculated. 5, 1 we've calculated. And 5, 5. Now for all the other terms. For row 1, column 2, only member 2 connects these two degrees of freedom. So member 1 won't contribute anything, as evidenced by the degrees of freedom shown here. So coefficient 1, 2 will be 0.667 EI per meter. Now for 1, 3. Those degrees of freedom are only connected by member 1. So our coefficient is 0.333 EI per meter. 1, 4 also comes only from member 1, 0.167 per meter squared. And 1, 6, which comes only from member 2. Then row 2. Row 2, column 1 comes only from member 1. Two comes only from member 2, since only member 2 connects at the node with degree of freedom 2. And 2, 3 we see will be 0 because no member connects degrees of freedom 2 and 3. 2, 4 will also be 0. And then 2, 5 will come from member 2. Two, 6 also comes from member 2. 3, 1. Row 3, column 1 comes only from member 1. 3, 2 we saw would be 0. 3, 3 comes from member 1. 3, 4 also comes from member 1. 3, 5 is given by this coefficient. and 3, 6 is 0 because no element connects the 2 degrees of freedom. 4, 1, row 4, column 1 will be this quantity. 4, 2 will be 0 because no element connects these 2 degrees of freedom. 4, 3 will be this quantity. 4, 4, 4, 5, and 4, 6 will be 0. So we have 0.167 per meter squared, 0.167 per meter squared, 5.56 10 to the minus 2 per meter cubed, a minus 5.56 10 to the minus 2 per meter cubed, and 0. Now row 5, we already pre-calculated 5, 1, so 5, 2 comes from member 2 and has this magnitude. 5, 3 is given by this coefficient. 5, 4 by this coefficient. Over meter cubed. We have 5, 5 already calculated because it had contributions from both members, and then 5, 6, which is this quantity. Now the 6th row. 6, 1, row 6, column 1 is given by this coefficient. 6, 2 by this coefficient. 6, 3 will be 0. 6, 4 will be 0. 6, 5 by this coefficient, and 6, 6 by this coefficient. So we have a minus 0.667 per meter squared, a minus 0.667 per meter squared, 0, 0, a minus 0.444 per meters cubed, and a positive 0.444 per meters cubed. And let's check. The diagonal is positive, and let's also check symmetry about the diagonal. And sure enough, it is symmetric. So that's a good sign. Now to partition our matrix. Our structure has only 2 unconstrained degrees of freedom, 1 and 2. So let's partition the matrix in between columns 2 and 3, and in between rows 2 and 3. This top left portion we'll call K11. That's different than this term. This was the individual coefficient. This refers to the entire chunk where we're talking about forces generated at unconstrained degrees of freedom due to deformations at unconstrained degrees of freedom. Now step 3. Let's find the fixed end forces. Let's start with member 1. We'll have a shear at each end, a moment at each end, and since there's no load applied in between, all of these little Q's are 0. Now member 2. Again, our structure, our beam, has shear at each end, moment at each end, but we have uniform distributed load in between. So these will not be 0. At the left end, for member 2, the moment will be Q1 for degree of freedom 1, not for fixed end force, and subscript 2 refers to it comes from member 2. On this side, we'll have the fixed end force Q, degree of freedom 2, not because it's a fixed end force, and subscript 2 refers to member 2. Our shear at the right end, Q6 naught, member 2, and at this end, Q5 naught, member 2. Now, to calculate these moments, let's look inside the back cover of our text. Fixed with uniform distributed load has moments that are omega L squared over 12 on each end. On the left end, they're counterclockwise. On the right end, they're clockwise. So for the left end, since we draw them counterclockwise, we have omega L squared over 12, and so that's 10 kilonewtons per meter times 3 meters squared over 12, and that gives a positive 7.5 kilonewton meters. At the other end, the fixed end force is going to be a minus omega L squared over 12, because in the inside back cover it's drawn clockwise, but our moments are positive when counterclockwise. Now if we consider this to be a free body diagram, of member 2 with fixed ends, we can sum moments about node 3, which is the right end, take counterclockwise as positive for my summation, and I get a contribution from the moment at the left end, a positive 7.5 kilonewton meters, a negative contribution from the shear at the left end, degree of freedom 5, acting through the length 3 meters, a positive contribution from the uniform distributed load acting over a length of 3 meters gives me the resultant at a distance 3 over 2 meters. And then we add in the moment at the far end, degree of freedom 6, which is a negative quantity. If I solve that, for for the fixed end force at degree of freedom 5, I get a positive 15 kilonewtons. Now let's apply vertical equilibrium. Choose up to be positive. We have the 15 kilonewtons shear at the left end minus the uniform distributed load acting over 3 meters plus the unknown shear at degree of freedom 6. Let's solve for the fixed end force at degree of freedom 6, and we get also a positive 15 kilonewtons. So for the structure, our Q naught for our 6 degrees of freedom is given by the 7.5 kilonewton meters, degree of freedom 2, negative 7.5 kilonewton meters, and this one would have had a contribution from member 1 because degree of freedom in 1 is common to both, but these were all 0. At degree of freedom 3, we have no fixed end force. Degree of freedom 4, none. Degree of freedom 5, we found to be positive 15 kilonewtons, and at degree of freedom 6, also a positive 15 kilonewtons. Now we are ready for step 4, where we find deformations. That is, the deformations at the unconstrained degrees of freedom. And in this case, those are degrees of freedom 1 and 2. To do that, we use the following relationship, where QK are the known forces applied directly to the degrees of freedom. In the case of this structure, those are all zeros. K11 we identified previously. D sub U refers to our unknown deformations, and K12 dk, where this refers to the chunk of the stiffness matrix referring to forces at unconstrained degrees of freedom due to deformations at constrained degrees of freedom, and these are the deformations at the constrained degrees of freedom. This would be things like support settlements. We have none, so that is 0. And at our unconstrained degrees of freedom are fixed end forces in global coordinates. But for a beam, global coordinates and local coordinates are the same. So let's start with the first equation. Force at degree of freedom 1. We said that's going to be 0 equals, and so we need our first coefficient, K1 little 1, which is 2EI over m, or over meters. And that's times deformation at degree of freedom 1, to which we add coefficient 1, 2, because we're looking for the force at degree of freedom 1 due to deformation at degree of freedom 2. and that's times the deformation at degree of freedom 2, and we add the fixed end force for the structure at degree of freedom 1, which is a positive 7.5 kilonewton meters. And this we'll call equation 1. If I look at the force at degree of freedom 2, again, there is no applied load directly to that degree of freedom, no couple moment applied there. And we need now coefficient 2, 1, which is this one. And we'll also end up needing coefficient 2, 2, which is this one. And so we have 0.667 EI over meter times deformation at degree of freedom 1 plus 1.333 EI over meters times deformation at degree of freedom 2 plus our fixed end force for degree of freedom 2, which is a negative 7.5. We'll call this equation 2. So we have two equations, two unknowns. So what I'll do is I'll multiply equation 2 by the following ratio, negative 0.667 over 1.333. And so when I multiply this entire equation by this ratio, the coefficient in front of deformation at degree of freedom 2, d2, becomes a negative 0.667. And so then I will add it to this equation, when I do that, this whole term drops out. So I get a 0 equals 2.00 minus, when I take this minus and this ratio times this one, what I'm doing is adding the two equations, but that's the negative sign there. I get a 0.333 EI per meter times the deformation at degree of freedom 1. These add up to 0. And then I have the 7.5 from equation 1, and I'll add this ratio times this quantity, but this ratio times this quantity then becomes a positive 3.75, and that's in units kilonewton meters. So if I evaluate each of those expressions, I have a 1.667 EI over meters times deformation 1 plus 11.25 kilonewton meters. So I can solve that for deformation 1, and I get a negative 6.75 kilonewton meter squared over EI. And then I'll substitute deformation 1 into equation 1. So I have 0 equals 2.0 EI over meters times the minus 6.75 kilonewton meters squared over EI plus 0.667 EI per meter times deformation 2 plus our fixed end force 7.5 kilonewton meters. And so I get 0 equals a minus 6.0 kilonewton meters plus 0.667 EI per meter times deformation 2. The EI's here canceled, one of the meters canceled, and we're left with units, kilonewton meters. Well, I can now solve this for deformation 2, and I get a positive 9.0 kilonewton meter squared over EI. Now the signs tell us important information about these results. We originally drew our anticipated elastic curve something like that. So our slope, or our rotation, is down here, clockwise, but counterclockwise would have been a positive slope, so we expect D1 to be negative. Here we have a counterclockwise slope, or rotation, and so we would expect D2 to be positive. Good. Those check. And now step 5. Let's find the member forces. And let's start with member 1. We're specifically looking for the shears, so I won't draw the moments. We're looking for Q4 from member 1 on the left end, and Q5 from member 1 at the right end. And we'll use equation 15-1, but I want to point out the equation's missing something. We need to add our fixed end forces back in order to obtain the member forces. Now, for member 1, the degrees of freedom associated with the member forces are 4, 3, because this is the near node, and this is the far node, 5, and 1, and therefore it has the deformations are also 4, 3, 5, and 1. So we're looking for 4 and 5, so I don't need to calculate 3 or 1, which means I don't need this row of coefficients or this row of coefficients. I can also save a little bit of time by recognizing that the displacement at degree of freedom 4 is 0. So it doesn't matter what these coefficients are, they'll each be multiplied by this 0. Likewise, the displacement at degree of freedom 5 is 0. So I don't need these. And since node 1 is fixed, there's no rotation, so this degree of freedom will also be 0. So I don't need any of these coefficients from the element stiffness matrix. I only need this one and this one. So Q4, the shear at the left end of member 1 is this coefficient times this deformation, d1, which we found to be this quantity. And to which we add the fixed end forces for member 1, and the fixed end force for member 1 is 0. So the shear at the left end of member 1 is a negative 1.125 kilonewtons. Up would have been positive, so it is in fact down. How about the other end? Q5 for member 1. In this case, we're looking to calculate this internal force. We didn't need any of these coefficients because each of those deformations were 0, so we need this coefficient, which is just minus the 0.167 EI over meter squared, times this deformation, minus 6.75 kilonewton meter squared over EI, plus our fixed end force for this member, which we found was 0. And that gives us a positive 1.125 kilonewtons. So it is indeed up. Now member 2. We're looking for the shears at the ends. On the left end, the degree of freedom is Q5 for member 2. At the right end, it's Q6, degree of freedom 6 for member 2. So again, we cannot forget that we need to add in our fixed end forces. My degrees of freedom for member 2 are near node Y is degree of freedom 5, near node Z being rotation is degree of freedom 1, far node Y 6, far node rotation or moment rather is 2. It should be moments because these are forces. And our deformations are degrees of freedom 5, 1, 6, 2 as well. Now I'm only looking for the forces, member forces at degrees of freedom 5 and 6, so we don't need 1 or 2, so I don't need these coefficients to solve this. And if we look at deformation in degree of freedom 5, it's supported there, so it's 0. So no matter what these magnitudes are, when we multiply them by 0, they won't contribute. So I won't look those up. We will get deformation at degree of freedom 1, but at degree of freedom 6, far node vertical deformation, it's supported, constrained, so I don't need these because they'll all be multiplied by 0. So I only need these 4 coefficients, all the same magnitude, just changing signs. And so let's write out finding the left end member force, the shear at the left end first. 6 EI over L squared for member 2 is 0.667 EI per meter squared. and that's times deformation at degree of freedom 1, which we found to be this, then we add, again, 6EI over L squared, so we have 0.667 EI over meters squared. Now times deformation at degree of freedom 2, which we found to be this, over EI, and to which we add the fixed end force, which for degree of freedom 5, member 2, was a positive 15 kilonewtons. When I evaluate this expression, add it all up, I get a positive 16.50 kilonewtons. Now the other end. Degree of freedom 6 for member 2. We have minus 6EI over L squared, so minus 0.667 EI per meter squared times deformation 1, to which we add a minus 6EI over L squared times deformation 2 and to which we add the fixed end force for degree of freedom 6, member 2, which was also positive 15 kilonewtons. So when I evaluate that expression, I get positive 13.5 kilonewtons. I believe we are now ready for step 6. We can construct the shear diagram from the internal forces we calculated. We'll label it V. It'll be in the units of kilonewtons. When we look back to our results for member 1, a positive shear pushes up on the left end, down on the right end. So this is drawn according to our sign convention for shear diagrams, and we have a negative quantity. On the right end, it's drawn in the opposite direction, so we need to reverse the sign. So that tells us that we're going to have a constant shear along the member, because it's going to start at a negative 1.125 and end at a negative 1.125. And it makes sense that the shear diagram is constant because there is no distributed load and no concentrated forces applied in between nodes 1 and 2. In member 2, again, we drew our shears as both up at the left end. That's in the correct direction for an internal force diagram. On the right, it's the reverse direction. So our shear diagram will be at a positive 16.5 kilonewtons at the left end of member 2, and we reverse the sign, it'll be at a negative 13.5 kilonewtons at the right end of member 2. So it jumps up and we should reach a positive 16.5, and it decreases till we reach a negative 13.5. In between should be linear because we have constant or uniform distributed load. And so we get a shear diagram that looks like that. Now step 7. Let's compare that shear diagram with our approximation. And so I'll redraw our approximated shear diagram here, and I'll label it as such. It'll still be in units of kilonewtons. As we look back to our step 1, we found that the shear was constant and 0 all the way across member 1, then jumped up to 15 kilonewtons, decreased linearly to negative 15 kilonewtons, and then closed out to 0. And as we compare these, remember when we drew our anticipated elastic curve or deflected shape, we said that there will probably be a small downward force at node 1, degree of freedom 4. Therefore, we expected the shear to not be exactly 0 as our approximation indicated, but to be a small negative quantity. And that's what we obtained. The shape is identical, and the magnitudes are relatively close. So I conclude that our shear diagram, constructed from our internal force results from the stiffness method, is reasonable. And now let's go back and review the process we followed. We started by conducting approximate analysis to determine approximate vertical reactions for the beam, and we assumed that the distributed load would go to the nearest vertical support, and then we constructed our shear diagram based on those approximate reactions and our knowledge of the applied loads. We then began the stiffness method by assembling the member stiffness matrices, first for member 1, then for member 2, and then we assembled the structure stiffness matrix, being careful to recognize that the degree of freedom sequence in the element matrices was not the same as the degree of freedom sequence we have for the structure stiffness, which is 1, 2, 3, 4, 5, 6. We then partitioned the matrix after we confirmed it was symmetric as a quick check against math errors, and we identified the chunk K11, which is the coefficients associated with forces at unconstrained degrees of freedom due to deformations at unconstrained degrees of freedom. We then found the fixed end forces for member 1 and member 2, added those together by degree of freedom to get the fixed end forces for the structure. We then used the stiffness coefficients and the fixed end forces to find deformations. And for this beam, since there are only 2 unconstrained degrees of freedom, we only need to solve a system of 2 equations and 2 unknowns. And I showed how to do that by hand, and we obtained the 2 deformations, and we confirmed that the directions of those made sense. and then we used those deformations with the element stiffness matrices, or actually part of the element stiffness matrices, to find the member forces that are the shears at the ends of the members. And we started with member 1, then member 2. We then used that information to construct the shear diagram, and then we compared it with the approximation that we created in step 1, and we found that our results from the stiffness method are reasonable. Well done.